Okay, let's go. So my name is Alex Leith, and I'm here to talk to you today about getting started with geospatial raster data. I've got a background in GIS. I went to university to be a surveyor, but decided that GIS was more fun. Did a lot of spatial tech, and including working with cloud computing systems. Ended up starting to write infrastructure as code, and then now for the last few years I've been working in Earth observation. I work at Geoscience Australia within a group there called Digital Earth Australia, and one of our big projects there is Digital Earth Africa. I'm also the chair of the local OSGeo Oceania organisation company, where we provide the central core around the Phosphor-G events in our region. And I work on the ODC Steering Council as well. So the plan here today is to introduce you to Earth observation data, and Sarah helped us do that in the previous presentation. I want to introduce the Open Data Cube. I want to talk about what Digital Earth Africa is, and then I'm going to go through death by live demonstration. So how to visualize raster data, how to analyze raster data, and then how to access raster data. At the end, I'll provide a link to all the materials that I've covered off in this presentation, and you should be able to go through and do the same thing yourself. So firstly, I'm going to talk about optical Earth observation data. So that means, as we heard in the previous talk, 6 common bands. So if I could just get folks to make sure you are muted. There's blue, green, red, near infrared, and shortwave infrared. These are the bands that have been captured by the Landsat group of satellites for the last 30 years. There's been 3 satellites that have captured data actively, 2 still capturing data, Landsat 7 and 8. Landsat 5 was retired. That data is at 30 meter resolution and has a 16-day revisit time. There's also a new program, the Sentinel from European Space Agency, and Sentinel-2 is optical satellites. There are 2 of them, Sentinel-2A and 2B, and they orbit on the opposite side of the Earth from each other, which means that they've got a 5D revisit time and 10-meter resolution. So it's higher spatial and temporal frequency for that, but they don't have the same depth of temporal data that the Landsat satellite has. Another common satellite data type is the radar data, so synthetic aperture radar, and ESA's Sentinel-1 satellites capture radar data. And we are working on getting that prepared for Digital Earth Africa. And there are some examples available in our sandbox notebook space. So we use the Open Data Cube to do a bunch of our data handling, to make it easier to work with this Earth observation data. And really briefly, Open Data Cube is a Python library and a Postgres database, which provides an index to data. So data can be stored on a local file system on your local laptop with a small install of the Open Data Cube, or it could be on an object store in the cloud, and it could be millions of files. Once you've got Open Data Cube installed and data indexed, you can use a Python application or a spatial web service or a web mapping visualization, which I'll demonstrate soon, to ask Open Data Cube what data is available for this spatial area and for this temporal group of time, and it will check in the database to find out where the data is and go and load it, load all the pixels and send them back to your application. Really briefly, Digital Earth Australia's history is that Australia used to be a downlink for Landsat data. Raw data was stored on tapes and put in the deep final repository. And eventually there was a project called Unlocking the Landsat Archive, where the tapes were digitized and a bit of software was written in order to make it easier to work with these data. That software was called the Australian Geoscience Data Cube. That software was later upgraded, version 2, had more general purpose aspects to it, and that was later renamed as the Open Data Cube. These days, Digital Earth Australia has ongoing funding to support government industry by making through making Earth observation data more easily accessible. Which brings us to Digital Earth Africa. Digital Earth Africa is a project that's built on the back of the success of Digital Earth Australia. We have funding from the Department of Foreign Affairs in Australia and from the Helmsley Charitable Trust in the US to make Earth observation data more easily accessible over the African continent. It's also about developing in-country capacity and has a broad range of applications, largely oriented around the United Nations Sustainable Development Goals. There are 20 people working on Digital Earth Africa, and we're right now hiring tech folks to build the core of the infrastructure of Digital Earth Africa so that it has people within the continent that will provide the continuity and ownership of this platform into the future. At the core, Digital Earth Africa is around being unopinionated. So we have opinionated services sitting on top of a bunch of data. We have the Open Data Cube and web services and a web map and a sandbox data science environment, metadata exploration engines. And so you can use these tools to explore the data or to do your science. You can also go around the back and just access the data directly. And I'll show you how to do that. So you can come in the front door, use the web services, or go in the back door and do it yourself. So what comes next is a bunch of live demos. And so what we're going to do is go down the abstraction layers. I'm going to start with visualizing data, and I'm going to finish on downloading and accessing data. So let's jump in. Here we have Digital Earth Africa web map. So once this application loads, we can see we have some data. So here we have the optical, simple red, green, blue, what your eyeballs see, as Sarah put it, a visualization. So this is not just a scene, this is all the scenes stitched together in a swathe. So this was captured a couple of days ago, and you can see there are areas of cloud and there are areas that are really quite pretty. And this is being rendered on the fly using the Open Data Cube off cogs that are stored in a cloud object store. So we can do really basic analyses on top of this data. For example, visualizing in false color, so highlighting a bit of vegetation, or using one of the standard indices, which is a band ratio between red and near infrared, to highlight areas in green, which have healthy vegetation, and areas in red, which are almost certainly not vegetation. This is a pretty simple visualization. We can look at the modified normalized difference wetness index, which is an index that shows a likelihood of being water, being wet, blue. And the data is not just available in this area. It's available for all of Africa. So if I go up to somewhere else, we can go and have a look in Cairo, near Cairo. Have a look at a completely different area, still captured on the same day. This is one of the aspects of Earth observation data which is somewhat inconvenient, is that it's spatially temporally sparse. And so you can't, just off the satellite, get data that covers everywhere. In a given day, there'll be 2 different passes with different satellites, and it'll be in different areas. But what I want to show you is doing some really simple visualizations of something where you can perhaps get a bit of value. So here, if we go filter by location, we can ask the web application to only show scenes that were captured covering this area, which means that in our date picker, we have dates that have data. If we click through every single day, there'll be some days where there's not a capture on in this site. So here we have a scene on the 5th of September, and we can jump back to a scene 5 days earlier on the 31st of October. And what I want to do is have a look at the vegetation index. And so then we can see what these irrigated areas are looking like in different time steps. The glory of live demonstrations is this awkward waiting thing that happens. And so there's 1 time step, 2 time steps, and 3 time steps. And we can keep going like that back through time, visualizing data. We can pick any time back through the last 4 years where there's data. So that is visualizing. And I'll share this presentation. You can have a look and visualize data yourself, or jump out now if you're quick enough to grab the URL. I want to talk about analyzing data though, because we're not just looking at a pretty picture here. We saw some beginnings of analysis in the visualization layers, the web services. But in order to do an analysis on Earth observation data, in my view, we need to have 2 things. We need to have data that's useful and data that's usable. Useful data has quality that can be used in analysis. If you want to compare an area, say in this year to last year, or in January this year to July this year, you want to be comparing like to like. And one of the big influences on what the apparent color of the Earth is from space is the atmosphere. So aerosols in the atmosphere interact with different wavelengths in different ways. And so we can model that and make data more better quality or consistent quality by removing those differences. That's called analysis ready. Once you do that processing, it's called making data analysis ready. There is 2 different sort of standard terminologies. Level 1 data is data that's had the terrain distortions removed, for example. Level 2 data has had these atmospheric effects removed in very simple terms. So my suggestion is that in order for data to be useful, it needs to be ready for analysis, or analysis ready. My next point is that it needs to be usable as well, and that means that we don't want to need to ask for data, wait for time, get data back, unpack it, see if it's okay. I'd suggest that we don't even want to have to download data and store it and collate it ourselves. We want to be able to access the data over the network, all of the data, all at once. And we can do that these days by storing data on cloud object stores and having it all available. To justify my point around analysis data, we have on the left here Landsat 8 scene, and on the left is a level 1, and on the right is level 2 data. These are both exactly the same image of the Earth. One's been processed to level 2, one just to level 1. This is the modified normalized difference wetness index, but what's important is that the scale in the 2 images is exactly the same, from -1 to 1. And on the left image, the level 1 image, it's highlighting cloud as being the most likely to be water. And on the right, it's highlighting the water as most likely to be water. What this sort of shows is that it's one of those garbage in, garbage out things. You may be able to get a good visualization out of level 1 data, but if you're going to do a serious analysis, you need to have level 2 data. You need to have good quality data. The usable, in my humble opinion, means Cloud Optimised GeoTIFFs. And what a COG is a standard TIFF file, a GeoTIFF file, so a spatially located TIFF with some optimizations in it to list the content of the file in the headers in a way that's predictable, so that you can request just a few pixels or a small area of the TIFF without having to download the entire file. Some of the files that we work with in Earth observation can be very large, and if you have to download all of them in order to do your analysis, it'll be quite inconvenient, as I'll demonstrate a bit later. And to just further justify what we're working on here, we're going from something which is an image, which is pretty, which our human eyes can see patterns in, but which isn't useful really for analysis unless you run something on top of it. And we're turning data into information here. We're going from something which is raw to something where you can say that's water, that's land, for example. We're doing an active analysis. All right, so before I jump into this next live demonstration, we're going to do this in the sandbox, the Digital Earth Africa sandbox. And this is a pre-configured Python environment built for data science. It has the Open Data Cube. It has a database with a bunch of data indexed into that database already. And it has a suite of Python libraries like Xarray and Dask and all of the really useful Python tools for doing visualization and plotting, all installed and working well together in it. And it's got a wide range of code snippets and examples. Might just pause before I jump into here to answer some of the questions. So have you experienced an upper limit of the size of a single Cloud Optimised GeoTIFF? You do need to be able to create the Cloud Optimised GeoTIFF on a computer that you own, and so you need it to not exceed the file system of the machine you've got. And some of the tools try to write it in memory, and so you might need lots of memory. But I'll show an example really soon of the digital elevation model of all of Africa, which is about 60 gigabytes compressed, so which is a pretty big cog. The next question is, what role does Earth Data Cube play in the entire stack, so the Open Data Cube? And as I explained briefly earlier, the Open Data Cube is used as a Python library that maintains and uses an index to make it easier to load data. It abstracts things. So in this image here, we've got an example of a query where we're saying, well, it's not a good one actually. I'll show you in a little while how it works from a usage perspective. All right, so doing data science. So here I have that example area that I was in before. And what I'm going to do is click on the map to just get the location here. And over here in our sandbox, we have an example which is using Sentinel-2 data. So I'll ignore all the intro. You can come back to this later, but we need to load some Python libraries. We need to load the data cube, which includes connecting to the database. And then we have a query. So we want lat long, which is north and east. Store that. And now we're going to use a datacube.load command, which is going to use all of these values to search for data that's available. So we're saying time, and actually I'm going to use August and September this year. We're using a spatial query, so X and Y, so longitude, latitude. So that's putting a bounding box around the area you want. We're defining an output CRS and resolution as well, because, well, that's technical. Let's not go there. Now, what we're going to do here is use something called Dask, which is a fantastic Python library that enables distributed computing. It'll actually also do a lazy load of this array. So arrays that we load end up being in a thing called Xarray, which is a very convenient storage Python library again. So these are Dask abstracted, lazy loaded arrays. But what we can see is the Open Data Cube has found 18 time steps, and we have 500 by 500 pixels of data that's available. We're going to do a quick load here because we want to just change the bands that we're loading. We're looking at 5 different bands here. And again, that's come back really fast because it hasn't loaded any data. But when we go to plot, because we are doing a function which actually wants to use the data, this is going to go and load the data and bring it back into the browser in the client and render it so that we can actually visualize what we're loading. So what's actually happening is we're going to render 4 images with red, green, blue band. So 4 times 3 is 12 different GeoTIFFs, 500 by 500 pixels being loaded out of each of them. And that should come back in not too unreasonable a time. And if you think about actually going and downloading those images yourself and combining that, which is actually what I'm going to do in a second, this is far more convenient. So what we have is 1, 2, 3, 4 images, and they're the 4 different time steps, the first 4 time steps that are available. If we do this plot down here, this is actually going to mask out these cloud areas, because once we've got data for analysis, we want to do an analysis on the ground, the pixels that are actually got valid data. We don't want to be comparing cloudy areas to not cloudy areas. And so this second function here is going to render these same images, but with the clouds masked out of them. So here the cloudy areas, or the smoky kind of areas, have been masked out as no data. So we can now compare this valid data with valid data. That's a really simple example. I've got one here which I've prepared earlier, and this one is showing a bit more of a trend in data. So what we can do is pick a field, draw a polygon, and we'll get 2 months of data coming out there. This is from Landsat, showing that field, or pick another field and compare the two fields together. This is extremely valuable when you start thinking about the real-time data, the Sentinel data that I demonstrated just before, which has got a 5-day revisit period. And so you can have a look at the field that you're working on and have a look at data that was captured maybe yesterday, maybe at worst 5 days ago, and have a look at these different trends in health in your field, or compare it to others. The last demonstration I've got here, which I'll go over really briefly, is around coastline extraction. So we have a case study area where loading data and calculating the modified normalized difference wetness index, which I showed before in the web map here. And what this does is it works out the boundary between the red and the blue. So it gets these lines, these white lines, extracts those and says that they're the coast, or likely to be the coast. Now we're combining these, this data with tidal data. So by loading tides and adding it to the X-array, which has the images in it, we've added a tide height parameter. And so at each of the images that are captured, we know how high the tide was. Now we filter those out to just get the high tides. And then we can combine all the high tides for 12-month periods. So 1, 2, 3, 4, 5, 6, 7 different years. And then we can extract the shorelines and have a look at how the shoreline has changed over these 7 years. That's at of those high tide periods. This is one of those examples of combining vector and raster data to build something which you couldn't easily do. We've used this in Australia also to extract elevation models by saying what is the tide, what height is the tide at the highest, 10%, and say it's 1.5 meters. And if you work out the shoreline, then you can say draw a contour line at 1.5 meters. We've demonstrated that you can get a sub-pixel resolution of these contour lines by doing that. I'm going to keep moving on and start talking about accessing data. So there's not an easy way to access data. So each of these scenes that I've talked about here, if you're loading one of these, all of the data is around about 1 gigabyte. We've got 1.5 million of those covering Africa for the Sentinel-2 data. That's 1.5 petabytes of data. Now you can use a command line to explore these buckets full of data. You can use an API, and so there is a Stack API that Matt Hansen from Element84 maintains on top of this data, and you can search data that way. Or you can start using web interfaces. Each of these has their different pros and cons. Whatever works for you is the right way to do it. What I want to do is really quickly load some Cloud Optimized GeoTIFFs into QGIS. So let's jump over to another area. And here is a bit of space that I've prepared earlier. So what we can do is load data from S3 into QGIS, and this is a public bucket, so we don't need credentials or anything like that. And if I add this, QGIS uses uh-oh, live demo fail. So I can load the Landsat. I want to try this again. Yes. All right. So what we've got here is approximately a 65 gigabyte GeoTIFF, which we can visualize. Just change the CRS over all of Africa on the fly, streaming like that fast. I'm going to change the visualization of it just to prove that this is working live. And I want to duplicate this Change this one to be a hillshade, so we've got something pretty. Well, worked okay. This file here, this is another example. This is one of the scenes. I'm going to demonstrate how I got this actually. So if we have a look at our web map here, we can show the raw data for a single scene. And there is a link here, which goes to a spatiotemporal asset catalog file, which was used to index this data. And if we pick, say, the blue band here, we can load this directly. Add that in. And this will go over the network and stream that data into QGIS as a, just over the network. So that's it there. And that's the area that we were looking at just before. And I guess my point is that that's a little slower, but much easier than downloading the data. All right, so running out of time. So I'm going to keep moving along. What you can also do is build a virtual raster from these links to cogs on S3. And then you can have a 3-band image that you can view in QGIS. I've done that earlier, but I'm not going to demonstrate that now. So this is what you can get up to, all without downloading any data. So what I want to talk about really quickly in the last couple of minutes is that you can do this. You can load a lot of Cloud Optimized GeoTIFFs off a Stack API into a neat environment where you can do all the things that I've just done on your own, the data science side of things. If you go to the Open Data Cube/Cube in a Box on GitHub, there's an example there how you can use the Stack API to index 1,743 data sets, and you can change it to index anywhere in Africa. And then you can load all the examples or the Sentinel-2 examples that I've shown in that environment and start working with that data, again, without downloading stuff. This is a real example that I just ran today, showing the data from September. So no tricks. And once you get bigger, this is a GIF showing every single pixel on all of the Sentinel-2 data over all of Africa that we've got available right now for all of it. On the left, we have cloud-free pixels, and on the right, we have all pixels. What this highlights is one of the challenges that we face in some of the work we're doing to build a cloud-free mosaic, which is that equatorial areas of Africa, there's areas that are cloudy all the time, nearly. And so it's very hard to get data without clouds. And this is where there's potentially value in the Sentinel-1 radar data, which can see through the clouds. And so it can be used in these areas to identify surface water, for example. So that's the end of my presentation. I've got a minute left, so let's dive through. Geospatial raster data is fun. Live demos, not so fun. Analysis ready data makes this useful. You can do analyses on top of that data. Cloud optimized GeoTIFFs on the cloud make it easy to use. Stack makes this, Stack being spatiotemporal asset catalog, that's why you're all here, isn't it? Makes it discoverable. And there's a slide in here with a bit of ancillary information that you might want to follow up on to dive into the data. And on this page, there's a training.digitalearthafrica.org is a link to a site where there is training material to onboard you into Digital Earth Africa's tools and systems, including the sandbox where you can run through the examples I've demonstrated and many more. Email us at Digital Earth Africa, email me at alex.leith@geotic.gov.au, find me on Twitter. We're on Slack in Open Data Cube, and we're a very welcoming community. So thank you very much for your time. I'm sorry I don't really have time for questions, but I'll stick around if there's anybody that's not jumping to the next session. Thanks heaps. All right, I'm going to go through the chat because people don't like unmuting. I'll keep talking to myself. GDALs, QGISs, VGRTs when dealing with large chunks of raster in memory. Does VSI curl differ from it? I don't think it does. And I've got to say that I have had a bit of trouble using VRTs in QGIS. I think it is slower than it probably needs to be, but it does work. All right, so Matthias has jumped into the next session. I really encourage you to go into his session, starting now. It started a minute ago, so dive in. What's a sensible internet speed to allow seamless processing via Python or QGIS? I think what you probably want to do, if you want to do that, is use one of these sandbox environments. It's a Jupyter notebook environment, and a fair bit of the processing will happen actually on the server, not on the client. And so if you have internet connections that drop in and out, then you'll still be able to do your work. Otherwise, it is large volumes of data that you need to push around, unless you're just doing a simple visualization. Cool. All right. Well, I'm going to leave it there. Please do jump into Matthias's Zoom. And thank you very much for your time and your attention. Cheers, folks.